pen, watch, bicycle, car, bus and bridge are all made of metals. On the other hand, helium, which makes balloons fly, and the carbon that constitutes diamonds are non-metals. What is the basis for distinguishing metals from non-metals? To understand the scientific basis for this classification, you need to examine the physical and chemical properties of metals and non-metals. In this lesson, you will learn about the properties of metals and non-metals. You will also learn how they form compounds and how they can be separated. At the end of this lesson, you will be able to define metals and non-metals, locate the position of metals and non-metals in the periodic table, discuss the physical and chemical properties of metals and non-metals, compare the properties of metals and non-metals. Metals are elements that have a tendency to lose electrons and form positively charged ions or cations. For example, sodium has an electronic configuration of 1s2, 2s2, 2p6, 3s1. During a chemical reaction, sodium can lose an electron to a non-metal like chlorine to form a sodium ion that has an electronic configuration of 1s2, 2s2, 2p6. Conversely, non-metals are elements that have a tendency to accept electrons to form negatively charged ions or anions. For example, chlorine has an electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p5. During a chemical reaction, chlorine can accept an electron from a metal like sodium to form a chloride ion. A chloride ion has an electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6. To get an idea of the properties of metals and non-metals, let's first locate them in the periodic table. When elements are arranged in the increasing order of their atomic numbers in the periodic table, metals, including alkali and alkaline earth metals, are placed on the extreme left of the periodic table. Non-metals are placed on the extreme right of the periodic table. Based on the positions of metals and non-metals in the periodic table, it is possible to predict their properties. For example, the elements on the extreme left of the periodic table are metals that easily lose electrons and are highly reactive. On the other hand, the elements on the extreme right are non-metals. They readily accept electrons and are also highly reactive. You will now learn about these properties in detail. If you look around, you will find metallic objects around you in various forms. For example, jewelry made of gold and silver, wires made of copper, and curtain rods made of aluminium are all metallic objects. Metals are used to make these objects because of some specific physical properties. Let's take a look at some important physical properties of metals. All metals are solids at room temperature, except mercury, which is a liquid. All metals are lustrous. Metal surfaces shine when they are freshly cut. For example, gold and silver are popularly used for making jewelry because of their luster. Metals have high densities and therefore tend to sink in water. For example, tin and lead sink in water. Exceptions to this rule are lithium, sodium, and potassium. The density of these elements is lower than that of water, and hence they do not sink. Metals are highly malleable and can be beaten into thin sheets. For example, aluminium and zinc can be rolled into thin sheets. This property makes them suitable for use in various industries like construction and manufacturing. Metals are highly ductile and can be drawn into wires. For example, copper and silver can be drawn into thin wires. Metals are good conductors of heat and electricity. Copper wires are commonly used in electrical cables because of this property. Metals have high melting points. For example, tungsten has a high melting point due to which it is used in bulb filaments. Mercury is an exception to this property since it has a low melting point. Iron rusts because it reacts with moisture to form iron oxide, which is commonly known as rust. Metals react with other elements in a variety of ways. Let's look at some such reactions. Formation of ionic compounds. Metals lose electrons to non-metals to form strong ionic compounds. For example, sodium loses electrons to chlorine to form sodium chloride, which is an ionic compound. Action of metals with oxygen. Metals burn in the presence of oxygen to form metal oxides, which are basic in nature. For example, a magnesium ribbon burns in oxygen to form magnesium oxide. Action of metal oxides with water. Metal oxides dissolve in water to form basic metal hydroxide solutions. For example, magnesium oxide dissolves in water to form a strong basic solution of magnesium hydroxide. Action as reducing agents. Metals have a tendency to lose electrons. In other words, they are good reducing agents. For example, carbon in the combined form accepts electrons from sodium and gets reduced to carbon in the free state. Thus, sodium acts as a reducing agent. Non-metals show properties that are unlike metals. That is, they don't possess metallic properties. Let's look at the common properties of non-metals. Non-metals exist as solids, liquids, and gases. For example, silicon and carbon are solids. Bromine is a liquid. Chlorine, fluorine, and oxygen are gases. Non-metals are non-lustrous, that is, they have a dull appearance. For example, the surfaces of sulfur and phosphorus do not shine. Most non-metals have a very low density. For example, oxygen and nitrogen are lighter than air. The exception is diamond, a form of carbon. Diamond is one of the strongest known substances. This is because carbon, in this form, has a very high density. Non-metals are non-malleable. For example, sulfur and iodine cannot be hammered into sheets. Non-metals, except for carbon fibers, are not ductile. For example, phosphorus and bromine cannot be drawn into wires. Non-metals are bad conductors of heat and electricity. For example, sulfur and phosphorus cannot conduct electricity. The exception to this property is graphite, which is a good conductor of electricity. Non-metals have low melting and boiling points. For example, sulfur and phosphorus have low melting and boiling points. When you make a bonfire, the wood burns to release smoke. The burning of wood involves a chemical reaction called oxidation. The carbon in the wood reacts with atmospheric oxygen to form carbon dioxide. The carbon dioxide is released in the form of smoke. Let's look at the chemical properties of non-metals in general to understand their behavior with other elements. Formation of covalent compounds. Non-metals form covalent compounds by sharing electrons. For example, in a molecule of hydrogen chloride, hydrogen and chlorine share a pair of electrons. Thus, hydrogen and chlorine are bound together through a covalent bond. Action with oxygen. Non-metals form acidic or neutral oxides. For example, sulfur reacts with oxygen to form sulfur dioxide, which is acidic. Nitrogen combines with oxygen to form nitric oxide. This nitric oxide is neutral in nature. Action of non-metal oxides with water. Acidic oxides dissolve in water to form acidic solutions. For example, sulfur dioxide reacts with water to form sulfurous acid. Action of non-metals as oxidizing agents. Non-metals have the tendency to gain electrons. That is, they are good oxidizing agents. For example, chlorine accepts electrons from hydrogen and oxidizes hydrogen sulfide to sulfur. In the process, it liberates hydrogen chloride gas. Thus, chlorine acts as an oxidizing agent. In ionic compounds, the forces of attraction between the ions of metals and non-metals are very strong. Therefore, it is difficult to separate the elements in such compounds. You can overcome this force of attraction or decompose this compound by passing electricity through it. The process of decomposition of a substance by passing electricity through it is called electrolysis. To understand how metals and non-metals are separated through electrolysis, let's consider sodium chloride. On passing electricity, sodium chloride splits into sodium and chloride ions. Sodium metal is deposited at the cathode. The non-metal chlorine gas evolves at the anode. Metals and non-metals exhibit a number of differences in their properties. Some of these important differences are: metals are generally solids, but non-metals may exist in solid, liquid, or gaseous states. Metals have very high melting and boiling points, unlike non-metals. Most metals are malleable, ductile, and lustrous, while non-metals are not. Metals are electropositive, that is, they tend to lose electrons, while non-metals are electronegative because of their tendency to accept electrons. Metals are good conductors of heat and electricity, while non-metals are bad conductors of heat and electricity. Metals form ionic compounds, while non-metals form covalent compounds. Metals form basic oxides, while non-metals form acidic or neutral oxides. Gold never rusts, because unlike iron, it does not react with atmospheric oxygen. This is because chemical reactivity varies across metals. Scientists have arranged metals in a series based on their chemical reactivity. In this lesson, you will learn about the arrangement of metals in an activity series based on their reactive properties. You will also learn how the positions of metals in an activity series impact the process of extraction from their respective ores. You will learn in particular about the extraction of aluminium from its ores. At the end of this lesson, you will be able to illustrate through an experiment the differences in reactivity of metals, analyze activity series of metals, describe various techniques for the extraction of metals, illustrate the process of reduction with examples, describe the process of extraction of metals by electrolysis, analyze the position of aluminium in the activity series, describe the process of extraction of aluminium from bauxite, and list the uses of aluminium. You can observe the differences in reactivity of various metals through an experiment. Take samples of 4 metals: sodium, magnesium, calcium, and copper in different test tubes, Add 2 ml of dilute hydrochloric acid or sulfuric acid to each of these samples. The reaction of the acid with the metal will yield a salt and hydrogen gas in each test tube. However, you will notice that the rate at which the gas is liberated in each test tube is different. For instance, adding 2 ml of dilute hydrochloric acid to sodium results in a vigorous liberation of hydrogen gas. If you hold a burning splinter over the mouth of the test tube, the flame is extinguished with a pop sound. Similarly, the addition of dilute hydrochloric acid to magnesium in the second test tube liberates hydrogen. However, the rate at which hydrogen is liberated in this case is lower than that observed in sodium. The rate of liberation of hydrogen reduces further in the reaction with calcium, while copper does not react with hydrochloric acid at all. The variation in the rate of liberation of hydrogen indicates that the metals differ in their reactivity. To predict the reactions of given metals with other elements, scientists developed a system where metals were arranged in decreasing order of their reactivity. This arrangement of metals is called the activity series of metals. Thus, in this series, the most reactive elements are at the top and the least reactive elements are at the bottom. For example, potassium at the top of the series is the most reactive among all the elements in the series. For any two metals in the series, the metal placed higher in the series can displace the other metal from its salt solution. For example, zinc displaces copper from copper sulfate solution to form zinc sulfate. As you move down the series, oxides of highly reactive metals like magnesium and aluminium are not reduced easily either by hydrogen, carbon, or carbon monoxide. This is because the ionic forms of magnesium and aluminium are more stable than their atoms. Moving further down, metals that are placed below copper do not rust easily because of their low reactivity. A number of metals are available only in combined forms as ores. To obtain the pure forms of these metals, we need to extract them from their respective ores. Based on the reactivity displayed by metals, they can be extracted through the following methods: reduction and electrolysis. Reduction is the process of removal of oxygen for extraction of metals from their oxide ores. The common reducing agents used for reduction of metal oxides are carbon monoxide, carbon, hydrogen. For example, iron oxide is reduced to iron by carbon monoxide. Iron oxide is reduced to iron using carbon as the reducing agent. Similarly, copper oxide is reduced to copper using carbon. Copper oxide is reduced to copper using hydrogen. The metals high up in the activity series are very reactive. Hence, they cannot be obtained from their compounds by heating with common reducing agents like carbon, carbon monoxide, and hydrogen. For example, a reducing agent like carbon cannot reduce the oxides of metals like sodium, magnesium, calcium, and aluminium because they have more affinity for oxygen than carbon. Therefore, these metals are refined by another method known as electrolysis. Electrolysis is the process of the decomposition of a substance by passing electricity through it in a molten or dissolved state. Consider magnesium chloride ore. Magnesium is highly reactive and therefore cannot be reduced by common reducing agents like carbon, carbon monoxide, and hydrogen. Therefore, magnesium is extracted by electrolysis. Electrolysis of fused magnesium chloride gives magnesium at cathode and chlorine at anode. During the reaction at cathode, the reduction of magnesium chloride occurs due to gain of electrons. Magnesium ions gain electrons forming magnesium atoms. During the reaction at anode, chloride ions get oxidized due to loss of electrons. Thus, chloride ions lose electrons to form chlorine atoms. Chlorine atoms combine to form chlorine molecules. Thus, as a result of electrolysis of magnesium chloride, magnesium metal is deposited at the cathode, and chlorine is liberated as a gas at the anode. Let's now take up aluminium, a well-known metal in the activity series, and analyze its properties as well as the method for its extraction. Aluminium is a highly electropositive element and so forms positive ions. Therefore, it is placed towards the top and below magnesium in the activity series. It is not viable to use carbon reduction as a method for extraction of aluminium because the metal needs to be heated to very high temperatures in this method. Therefore, aluminium is extracted from its ores using electrolysis. Important ores of aluminium are bauxite, represented by the formula Al2O3 2H2O, corundum, represented by the formula Al2O3, and cryolite with the formula Na3AlF6. Bauxite is the principal ore of aluminium. The extraction of aluminium from bauxite involves 3 steps. First, the purification of bauxite using Bayer's process. Next, the electrolytic reduction of anhydrous Al2O3 by Hall and Herold's process. The last step is the purification of impure aluminium by Hope's process. The first step in the extraction of aluminium is the purification of bauxite through a process called Bayer's process. This process is named after Austrian chemist Carl Bayer, who invented and developed the method to supply alumina for the textile industry. Iron oxide is present as an impurity in bauxite. In Bayer's process, this iron oxide is removed by treatment of bauxite with sodium hydroxide solution. Purification of bauxite involves 3 steps. In the first step, aluminium oxide is allowed to react with sodium hydroxide to form sodium meta-aluminate. In the second step, sodium meta-aluminate is diluted with water to form aluminium hydroxide. In the third step, aluminium hydroxide is heated strongly to form aluminium oxide. The second step in the extraction of aluminium is the electrolytic reduction of alumina, obtained using Bayer's process. This is done through Hall and Herold's process. Hall and Herold developed the process independently. The electrolytic cell used in this process has the following components: an iron tank lined on the inside with carbon, which acts as the cathode, a series of carbon rods that act as the anode, alumina, Al2O3, as the electrolyte. Fluorspar and cryolite are mixed with the electrolyte to increase its electrical conductivity and decrease the fusion temperature. In the electrolytic process, electricity is passed through the electrolytic cell. Sodium, aluminium, and calcium ions migrate towards cathode. The aluminium ions discharged at the cathode sink to the bottom of the tank and are periodically tapped off. The oxide ions lose electrons and form oxygen atoms at the anode. The oxygen atoms combine and form oxygen molecules. The metal obtained after Hall and Herold's process is about 98% pure. This needs to be purified further. The third step is purification of the electrolyzed output from Hall and Herold's process. This is done by using a cell developed by Hoop. Therefore, the process is called Hoop's process. Hoop's cell consists of an iron tank lined at the base with carbon, 3 layers of molten aluminium with different densities to prevent their mixing. The upper layer of the electrolyte cell consists of pure molten aluminium with a series of carbon rods that serve as the cathode. The middle layer or the electrolyte layer consists of a molten mixture of sodium, barium and aluminium fluorides. The third layer is the bottom layer. Along with the carbon lining, it acts as the anode for the electrolytic cell. The bottom layer contains impure molten aluminium obtained from Hall and Herold's process. Using this cell, aluminium is purified in 4 steps. Electricity is passed through Hoop's cell. Aluminium ions from the middle layer reach the top layer and get discharged. Aluminium ions collect at cathode as pure aluminium. At the same time, an equal amount of aluminium from the bottom layer, that is, the anode layer, moves to the middle layer. In this process, 99.98% pure aluminium is obtained. Aluminium is used in a wide range of products, from chocolate wrappers to sophisticated aeroplanes. Let's take a look at some of its common uses. Aluminium is widely used in the manufacture of automobile components because of its strength and relatively lighter weight. In the construction process due to its high tensile strength. In the manufacture of electric wires due to its high conductivity. For the packing of medicines and pharmaceutical products due to its malleable nature. In the manufacture of soft drink cans and espresso coffee makers because it does not rust and is relatively less toxic in nature. In the manufacture of kitchen utensils because aluminium is a good conductor of heat. Extracted aluminium in combination with other metals like copper, manganese, magnesium form alloys. An alloy is a homogeneous mixture of solid solution of 2 or more metals or metals with non-metals. Duralumin is a light and tensile alloy of aluminium. Duralumin is composed of 95% of aluminium, 4% of copper, 0.5% of manganese and 0.5% of magnesium. Let us look at some of the common uses of duralumin. Duralumin is widely used in the aircraft industry. This is because of its lightness and other desirable physical properties. It is also used in making pressure cookers to withstand high temperatures. Magnesium is an alloy of aluminium and magnesium. Although weak and soft in elemental state, magnesium combines with aluminium to produce some alloys that are useful in engineering materials. Magnesium is composed of 85% of aluminium and 15% of magnesium. Magnesium is used in the making of balances because of its high structural strength and resistance to corrosion. It is also used in the making of optical instruments like cameras and microscopes due to its light weight and resistant to corrosion.